A vertical or horizontal spring, the energy just oscillates back and forth between kinetic and spring potential energy. For a horizontal spring, so our total energy, our mechanical energy, is Ke plus Pe, and that's just 1/2 mv squared plus 1/2 kx squared or y squared, depending on whether we're vertical. The difference being, again, if we're horizontal, we're talking about where the spring is stretched from its equilibrium position. Vertical, it's kind of the same thing, but our equilibrium position is where our gravitational and spring forces are balanced. Okay. If we plug in our values from our simple harmonic motion, our velocity is minus a omega sine omega t, and our position squared is a cosine omega t. So let's see what we've got here. If we, here we have, well, let me just distribute that squared. We have m a squared omega squared sine squared omega t plus 1/2 k a squared cosine squared omega t. The thing is, m omega squared, remember omega is square root of k over m. So if we plug that in, we've got omega squared would be k over m, and the m's cancel out. We got 1/2 ka squared sine squared omega t plus 1/2 ka squared cosine squared omega t. So at any given time, this right here is our kinetic energy, and this right here is our potential energy for an oscillating spring. We can use those expressions to find potential energy or kinetic energy individually. And then going further, sine squared plus cosine squared is 1. So our total mechanical energy is just 1/2 k times amplitude squared. So we have this much total energy all the time, but that energy oscillates between kinetic energy and potential energy. There's a nice graph on page 431 and 432 in your book. There's some nice graphs that show this oscillation of kinetic and potential energy. So, as an example problem here, a vertical spring with constant 55 newtons per meter has a 2.1 kilogram mass suspended from it. The spring is compressed 12 centimeters from where it hangs at rest and released. So, we've got a mass, and it's picked up 12 centimeters from its starting position and then dropped. If it was pulled down instead, the only difference would be that normally our x is this a cosine omega t, but if it was pulled down, then it's at a minimum first, and so our x would have to be a minus a cosine omega t. So keep those sorts of things in mind. So position is a function of time. X is a cosine omega t. Since we're going to be doing stuff with energy, I'm going to make this into meters. So our a is 0.12 cosine. Omega, remember, is square root of k over m. So it's cosine of square root of 55 over 2.1 times d. And this is the position as a function of time. I guess I should call this y since it's a vertical spring. It's y of t. What is that? Okay. Determine kinetic energy at t equals 3.1 seconds. Well, we've established that kinetic energy is 1/2 k a squared cosine squared omega t. So that's 1/2 55.12 squared cosine squared of root 55 over 2.1 times 3.1. So I punch that in, make sure I am in radian mode. I am in radian mode. 0.5 times 55 times 0.12 squared times cosine of 3.1 times root 55 over 2.1 parentheses squared. And kinetic energy at that point is 0.386, etc. joules. Find the total mechanical energy. Well, total mechanical energy is just 1/2 Ka squared. And that's simple enough to punch in 1/2 55 times 0.12 squared. 0.5 times 55 times 0.12 squared. That's equal to 0.396 joules. So we can tell at 3.1 seconds we're close to the maximum amount of kinetic energy. Remember, when a spring is oscillating back and forth, it has maximum kinetic energy at equilibrium, and the maximum potential at its furthest stretch and compressed points. The speed when the mass passes through equilibrium, well, there are a couple different ways we could do this. We could use our velocity equation. We could say that v is minus a omega sine omega t, and when it passes through equilibrium is when this sign is 0, so we could say v equals minus a omega. That's one way of going about it. We could also say that we know when it passes through equilibrium, its kinetic energy is equal to the total mechanical energy, which is 1/2 Ka squared. So and then set that equal to our 1/2 mv squared. And these two are equivalent because this just gives us v equals, divide that, it's a times root k over m, and here we had a omega, and omega is the same thing as root k over m. So any way you slice it, it's 0.12 square root 55 over, where's the mass, 2.1, punch that in, and get 0.614 meters per second. That's just an example of some of the questions I would ask you involving the mass on a spring.